So what do these elements correspond to in the case of Kruskal's algorithm? Right, but what are they initially? Initially, these E1, E2, what are E1, E2, E3? These would be the vertices, the initial vertices. Right? Now, what are the operations that we have to do on this collection of disjoint sets? Right? One operation is union. Right? The operation of union has to be done when I have one connected component. Right? I have another connected component, and the edge that I add runs between these two connected components. Then the resulting thing would be this entire thing would be one connected component. Yeah, and it should get reflected here by taking the union of the corresponding sets. So I have to do an operation of union. That's one operation under which I have to maintain this collection of disjoint sets. So what do I mean by that? Suppose this collection has E1, E3, and E7 in it, and this set has E1, E3, and E7 in it. This has E2, E5, and E9. Then after the union, I should not have these two sets in my collection, but these two sets in the collection should get replaced by one set, which is E1, E2, E3, E5, E7, and E9. Yeah. The other operation that I have to do is, right, so given an edge, I have to look at the two endpoints of the edge and determine if they belong to the same connected component or not. Right? So the endpoints of the edge would be the two elements, and I have to check given two elements whether they lie in the same set or not. Right? So we call that an operation of find. So what does find do? Let's say find takes as parameters two elements x and y and returns true if x comma y are in the same set. What should it return? Well, this is not a complete description of find. If x and y are not in the same set, what should find return? Fine. It should return the two sets in which those two elements lie. Why should it return the two sets? Because then we need to do the union on those two sets. Exactly. Right? So union should take as parameters two sets, let's say S1 and S2, and should take the union somehow. Right? This is what we require of our data structure. So this is not a accurate description of find. I will have to modify it, but you understand the need for returning the sets in which the two elements lie. Right? So instead of find x comma y, let me have just an operation called find x. Yeah, returns the set in which x lies. There's a unique set in which x lies because our collection of sets is always a partition of the universe. Right? So there will be a unique set and we want to return that set. Then how will we implement this operation? We'll do a find x, we'll do a find y. If those two sets are the same, then we will conclude that we are forming a cycle. If those two sets are different, then we will take the union of those two sets. Yes? Right? Everyone following what? So if I were to write down Kruskal's algorithm now, it would look like this. So with this, assuming that these two operations exist, it would look something like this. So what are the steps of Kruskal's algorithm? First, sort the edges. Sort the edges in increasing order of lengths. And let's say this ordering is E1, E2. Please do not confuse between this E and the element E that I had in the previous. Fine. Union of those two sets. This. So right, these E correspond to edges and the previous one was elements, right? So we'll keep these separate. Okay, now what should I do? For I equals 1 to m do. So a universe of elements like EI equals u comma v, which means that u and v are the two endpoints of the edge EI. What is it that I have to do? If find u equals find v, then it forms a cycle. Then we don't have to do. So I should really do not equal. If find u is not equal to find v, then t is t union EI. So I should have some t initialized to null. Yeah. And what else should I do? Union find u find v. Yes. Right. Of course, I need to initialize this selection of disjoint sets. So I would have, when I create this collection of disjoint sets, it will get initialized to, what will it get initialized to? Singletons, right? So each element in the collection would be the singleton vertex. Okay. So this would be what the procedure would look like now. We need to understand what kind of a data structure to keep for the find and what kind of a data structure to keep for maintaining the collection of disjoint sets so that these operations can be done very quickly. How many times do we do the union operation? And how many times do we do the find operation? Yeah, number of unions? Like, because every time I do a union, I include an edge into my tree. How many edges can there be in my tree? Exactly n minus 1. So I'll have exactly n minus 1 unions. How many finds will I have? Right? For every edge I consider, I have to do 2 finds. In the worst case, how many edges will I consider? All the m edges. No more. Right? So number of finds is less than or equal to m. Okay, let's make it not equal to 2m. Okay, I have said for I equals 1 to m, but you can always break out of this procedure the moment you form a tree. Right? So if you form a tree before, you can break out of this procedure, of this for loop, right? So you'll keep it less than or equal to 2m. Okay, so what will be the total running time of this procedure then? If this operation, let's say, takes u time and this time takes f time, then what's the total running time? Anyone? This step will take m log m time plus u times n plus m times f. Yes? So now we have to find out a good data structure. By good we mean we should do the u and which will have a small u and small f. Is everyone comfortable with this? Are there any questions to this point? Okay. Can someone suggest a data structure to me? How will you maintain this collection of disjoint sets? Linked list, right? Let's say linked list. You are at the end of the course, but you can't think beyond linked list. Huh? So how will we have? We will have as many linked lists as the number of sets. Is that what you want to have? So one linked list for each set. Okay. No, let's complete this first. How much time does union take and how much time does find take? Union can be done in constant time. Right? अगर आपकी linked list बड़ी भी होगी है, right? So let's say we keep track of the front and the end of each linked list. If we do that, then I can combine two linked lists in constant time. Yes. So union will not take too much time, but how much time does find take? Or the size of the linked list, which in the worst case could be n. Yeah. Now is that good? If we were to do this, we will take mn time, which is too large. We are looking for a time complexity of something like m log m. Right? So if you're looking for something like m log m, this quantity should be no more than log m, and this quantity should also be no more than log m. We can permit it to be as large as log m. Yeah. So this is not too good a data structure. Someone had another idea. What was your idea? A tree. What will we do with a tree? How will we use a tree? Heap. Heap. What will you do with the heap?
For checking if two things belong to the same set, we check the minimum of the heap.
Okay.
And by union, we can merge the two.
How much time does it take to merge two heaps? Order n. Height of the heap. Why? Why does it take? If I have two heaps, why does it take order h time to merge them? Huh? Does it? If we do that, then I can compare the structure. By good we mean we should do the u and which will have a small u and small f. Right? Can someone suggest a data structure to me? But you can't think beyond linked list. Huh? Of disjoint sets. Linked list. Right? Let's say linked list. You are at the end of the course, but you can't think beyond linked list. One linked list for each set. Okay? The following operation. So this is a collection of disjoint. Right? Right? Why does it take? If I have two heaps, why does it take order h time to merge them? Huh? Does it? Order smaller? No. Number of elements is smaller, but that could be as large as n by 2, right? Okay. What else? Okay. So we'll have a new data structure for doing this. Yeah? And what will our new data structure be? I'll just show this thing to you, and then you'll understand what's happening. So suppose my universe was A, B, C, D, E, F. 6 elements. Simple. Right? So initially, recall that what are the sets in my collection? The singletons A, B, C, D, E, F. So I have A, I have B. So I have one node for each of these 6 sets. Now suppose you say union the set containing A, right? So you will say something like union find A, comma find B. The set containing A and the set containing B. So what I'm going to do is to make one of them. So each of these nodes has only one pointer with it, or a reference, right? So it has a data field and one reference field. So I'll make one of these guys point to the other. Okay. So the next step I will have, when after I do this, this is what my collection looks like. These of course remain like as they are. Okay. Now suppose you were to say the same thing: union find A, comma find C. So when I say find A, I'll start from A and keep going up till I hit the root. So this is now the root. How do I know it is the root? Because its pointer points to itself, let's say, or it's null or whatever. Yes, when we do the union, so you'll understand this, as we proceed. So this is what the trees look like. So each one of them is a tree. Right now this tree has only one node in it, but this tree has 2 nodes in it. And now the pointers are going up. We just have parent pointers, so to say. When I say find A, I'll start from A and keep going up the tree till I reach a node. Let's say its parent pointer is either null or it's pointing back to itself. Right? At that point I know it's the root. And so this says that find A, the element A is in the set whose root or in which B is. So I come to B. So this is the element. This is the set in which. So what we are doing is that for each set, how do we represent a set? So each set is represented by one of the elements in the set. Yes. Which is in this representation, it will be the root of the set. So in some sense, all the elements of a set elect a leader. Yeah, and this is the leader of that set. So A and B are the only 2 elements in the set. The leader is B. So when I say find A, it returns to me a reference to this node, which says that this is the root of the set in which element A lies. When I say find B, what will it return? The same thing. And then I can compare those two and determine that they are in the same set or not. Okay. So what find A, find B returns are the roots of the corresponding trees. Okay. You'll understand this as we proceed. What union does is it takes the root of these 2 trees and links them up, makes one point to the other. Right. So for instance, here I may decide to make B point to C, in which case my new representation would look like this. Yes. Okay. Now if I were to do a find A, what will be returned when I do a find A? A reference to C, a reference to this node. And when I do a find B, what is returned? A reference to same node. So I can compare these two. So I can return a C or I can return a reference. Actually, it's best to return a reference because then that can be used by the union operation.
So what is C wasn't alone?
What do you mean C wasn't alone? Okay, C wasn't alone. I understand what you mean if C wasn't alone. We come to when C is not alone. Yeah. So all we're doing is taking the roots and merging them. So suppose at this point I did another operation which was union, find D, find E. Yeah. So what will I do? I'll link up the roots for D and E. So let's say I decide to make D point to E. Yeah. Now as you can see, D and E are not alone. So if I decide to do an operation like, right, so let me keep this picture there. And if I were to do, let's say, union, or let me write it down here, union find A, comma find D, then what does find A return? It returns a pointer to C. D returns a pointer to E. I need to link up these 2 roots. So I can make C point to E or I can make E point to C, whichever I please. Let's say I decide to make C point to E. Okay. This is what I would get then. And of course, F would be sitting on its own. Yeah. Everyone understands what the procedure is. Yeah. So you understand what the find operation is. What does find operation do? It starts from the element and keeps tracing the pointers up till it hits the root. Exactly. So you have a list of vertices. Right? So when I have an edge, I have its 2 endpoints, I have the vertices, and from that vertex list, I might have references to this node. Right? Recall you have a data structure for your graph, right? In which you have an array. So suppose I had an adjacency list representation. So this array would contain my list of vertices. Right? I could have another reference from here to this node here for every. So if this was node vertex B, so I could have another reference from here to here, so that I can access this quickly. Right? This is just referring to this particular node, and so this will always remain the same. There's no problem with that. Right? So what's the problem with this implementation? So how much time does union take? So union takes now as input references of 2 root nodes. Right? And so all it has to do is to modify one pointer, one reference to point to the other, to refer to the other one. Right? So union takes order 1 time. But how much time does find take? Find would take a lot of time because it might have to go through a very long list to reach the root. In the worst case. Right? Can you construct a sequence of unions in which this would happen? Right? I decide first to merge AB, then AC, then AD, then AE, and AF. And if you were to doing the union in this order, then things would go back. Yeah? So we have to do the unions in a more clever manner. Huh? Fine. No, we'll do the union in a clever manner. Right. So recall that when we were linking elements, we had an option. Either make one point to the other or make the other point to the first one. Yeah. So now we will exploit that. Okay. So I'm going to use a rule called union by rank, in which if I have two trees, right, and suppose this has n1 nodes in it and this has n2 nodes in it, then I will make the lighter tree point to the heavier one. So without loss of generality, let's say n1 is less than n2. So then I'll make this point to that. We'll make the lighter point to the heavier. Right? Now you'll not have this kind of a scenario in which if you had these, let's say, 6 elements, first you made this point to this, right? And then when you're trying to combine this and this, you'll not make this point to this anymore. What will happen now? You'll make this guy point to this. And now this tree has 3 nodes in it. So if this combines with this, you'll make this point to this, and this point to this, and this point to this. Right? So that now, what is the height of this tree that I get? 1 only. Right? And so find will take very little time. Okay? So we have to see that if we use this rule, what can be the height of the tree in the worst case? How high can the tree become? Right? How high can the tree become if we use this rule? Anyone? Log in. Why?
Because we get the time procedure. That will be the pairs of n by 2 each.
You're trying to construct a worst case, but that need not be the way we do things, right? Or that need not be the worst case. How will you argue that this rule of union by rank will lead to trees which have height? So what's the claim we want to make? No, not the height is minimum. A tree with n1 or n1 nodes, let's say, has height less than or equal to log of n1. Suppose I have to prove this claim. A tree with n1 nodes, so at any point, if I have a tree with n1 nodes in it, it has height at most log of n1. Okay? Prove कर सकते हैं आप इसे by induction. Good. So let's use induction. I'm not going to write down the proof formula, but I'll tell you what the procedure is. So I'm combining two trees, one n1 nodes, the other n2 nodes. Without loss of generality, let's say n1 is less than or equal to n2. Yeah? Let's assume that the induction hypothesis is true till this stage of my procedure. That means that इसकी height is less than or equal to log of n1. And इसकी height is less than or equal to log of n2. ठीक है? Everyone with me? Now we have to show that as a consequence of this, I'll get a new tree with how many nodes in it? n1 plus n2 would be the number of nodes in the new tree. So I have to argue that its height is no more than log of n1 plus n2. Let's see whether that is true. Yeah? So what are the two cases? n1 strictly less than n2. What will be the height? No, what will be the height? The height would be, so height of resulting tree is either the height of this tree, so we have done this. It's either the height of this tree or it is the height of this tree plus 1. Yeah? So height of resulting tree, अगर इसकी height h1 है और इसकी height h2 है, so height of resulting tree is less than or equal to max of h2, h1 plus 1. It can take a value of h1 plus 1 also. h2 और h1 equal होंगे ना, n1 और n2 equal होंगे. Oh, the height of resulting tree, okay, fine. Equals max of h2, fine. Okay. Now, let's see. This is the height of the resulting tree. If this value equals h2, there are two possibilities. Either this value is equal to h2, but h2 is less than log of n2, which is less than log of n1 plus n2. The other possibility is this quantity equals h1 plus 1, which is less than or equal to log of n1 plus 1, which is equal to log of 2 times n1, which is less than or equal to log of n1 plus n2. 1, because n2 is greater than or equal to n1. So actually we have not used the fact that n1 is strictly less than n2. Have you used the fact? Yeah, so it will become equal. That's okay. Right? So I don't really need this. So what I said, one of the trees has lesser or equal number of nodes than the other. If they're equal, actually you can connect it anyway. Right? So again, one point to the other. This by induction hypothesis is height at most log of n1. This is height at most log of n2. Yeah. Now what is the height of the resulting tree? It's either the height of this tree or it's the height of this tree plus 1. If it's the height of this tree, then it's log of n2, which is less than or equal to log of n1 plus n2. If it is this tree plus 1, the height of this tree plus 1, then it is log of n1 plus 1, which is log of the same as log of 2 times n1, which is less than or equal to log of n1 plus n2, because n2 is larger than n1. This is the base case true. Huh? When n equals 1, the height becomes 0. Let's define the tree of 0 with only one node as having height 0. Okay? If n equals 2, this becomes 1, which is okay. When you have 2 nodes in the tree, it has height 1 then by definition. Okay? So now what are we saying? If the tree has only one node in it, this is height 0. If this is the case, it has height 1. So I'm counting the number of edges on the longest path from one of the leaves to the root. I'm counting the number of edges, not the number of nodes. Everyone with me? So what does this show? So is this a complete proof? What am I doing an induction on? Number of nodes in the tree. Right? So assuming that the statement is true for all nodes of certain less than a certain number, I can say okay, it's true for this. When I link this and I get a tree with larger number of nodes, it will continue to be true. Okay, great. This is called union by rank. Rank meaning the rank is the number of nodes in the tree. You can also do a union by height, as in you can make the shallow tree point to the tree with larger height. That will also work. Let's see why. Right? What am I doing now? This is the tree of height h1. This is the tree of height h2. h1 less than or equal to h2. I do this. I make the root of h1 point to the root of h2. I'm just showing you two alternate ways to do the same thing. Okay? Now what should my induction statement be? How will I prove? What is the claim I should try to make? What holds true? So a tree of height h, what should I try and prove? A tree of height h has at least 2 to the h nodes. Good. Yeah? This is the converse of the claim. There we are talking of a tree with so many nodes has height at least log of h. Here if the height is h, then it has at least 2 to the h. At most. It has height at most log of n1. Right? It is not possible. How do we prove this? Once again induction. Suppose claim is true for all trees of height h1 plus 1 once again. Why is this one? This is also greater than or equal to max of 2 to the h2 comma h. Okay? Right? The proofs are very similar if you get it more than limit already. So if it has height more than log n, it will have more than. Constant time? Yes. So something has to be done more. And what is it that has to be done? In the root node, we have to keep track of either the height or the number of nodes, whichever it is. And this is an information which is not difficult to maintain. Right? Because when I do a union, this value is updated to either the height. If you are maintaining the height, it becomes the max, or if you are maintaining the number of nodes, you just add this quantity to that. Right? So how much time does union take now? Constant time. Because you just have to update this variable, right, and do this reference update. How much time does find take now? Right? I start from a node and I keep moving up the tree. Since the height of the tree is never more than log n, find takes no more than log n time. Okay? Right? So the total time taken by Kruskal's algorithm then becomes time for sorting n log n plus how many unions did we say we need? At most n unions. Every time I include an edge, I need one union. Since each one of them is taking constant time, this is just order time. How many finds do I need? For every edge, I might need 2 finds. So m times log n. Yeah, what is this? M log n. M log m or m log n? What is log m? n की maximum value कितनी हो सकती है ग्राफ में कनेक्टेड ग्राफ? n की maximum value कितनी हो सकती है? n की maximum value कितनी हो सकती है? n square. So log n की maximum value is 2 log n. And minimum value, n की minimum value कितनी होगी कनेक्टेड ग्राफ? Log of n. So log m and log n are the same thing. Log m is theta log n. Yeah, they are within constant. So whether I write log m here or log n here is immaterial. Yeah, they are the same quantities. Okay, so I will The next thing I want to do is to show you one way of improving the union find data structure. Yeah? So we saw the method. So one way, so this data structure we said if you do union by rank, then the time required for find improves. Yeah? It becomes order log n. You can further improve the time required for find by using a technique called path compression, whose analysis we are not going to do in this class, but you will learn in your algorithm course. Okay? So what is the technique? So it's just the following. You have your tree. Algorithm source. Compression is order log n. You can further improve the time required for find by using a technique called path compression, whose analysis we are not going to do in this class, but you will learn in your algorithm course. Okay? So what is the technique? So it's just the following. You have your tree in which you are doing a find. मान लीजिए आपका ये नोड है. आपने क्या किया? आप यहाँ से यहाँ गए, यहाँ से यहाँ गए, यहाँ से यहाँ गए, और आप यहाँ से यहाँ चले गए. ठीक है? So you went up the tree like this to do this find. Now the question is, why don't we do something at this point so as to improve the performance of future finds? You might have to find this node again. Yes? Yes. So we will modify these things. We will make this parent pointer point straight to the root. And not just this guy, everyone on this path. Why are we doing this? Anyone? Because now these guys become closer to the root. What is, I'm not drawing the rest of the tree, but now you can see that this node is this. This, let me put a dot here, is this guy, connected with just one link to the root. Let me put a cross here. Yeah, and this last one without anything is this. Of course, there are subtrees hanging down here. They will continue to hang down here. Right? Because there could be other nodes pointing to this. So they continue to. But when I later, so what are we doing as a consequence of this? We are bringing the nodes closer to the root, thereby reducing time to the tree, and that reduces the number of the time required to do your find. No, the root is not changed of this tree. The root of this tree remains as before. Oh, union by height. You are worried about if the union procedure requires height. Height. Huh? मेरे क्वेश्चन समझ नहीं आया. आंसर में बात. The root, right? Of this, the root of this tree will point to the root of the other tree. Huh? No, these will not change then. These will not change. We are not going to change these now. Right? If I take the union of this with someone else, that's okay. I did that. I'm not going to change these pointers. I'm not going to change these pointers. Right? So if you are adopting this procedure, then union for the union operations, you should not work with height, but with number of nodes. You understand why? Because we are changing the height of the tree by doing this. Right? And we might be changing it in a manner which might be hard to recompute. Right? After I do this path compression, right, maybe this was the node, there was a leaf here which was the furthest from the root. When I change this, the height of this tree changes. But how do I now compute the new height of the tree in constant time? Very difficult. So we use the union by number of nodes. So that's the procedure we are going to use. Right? So the metric will be which tree has lesser number of nodes. The tree with lesser number of nodes will be made to point to the tree with larger number of nodes. Or the root of the tree with lesser number of nodes will be made to point to the tree with the root of the tree with larger number of nodes. Okay, everyone follows this? Questions? What we are doing in? What are we doing in path compression? What we are doing in path compression is that we say, okay, when I am searching for this node, when I am doing a find operation on this node, I am in any case going to travel all the way up. Right? I am going to traverse this link and I am going to traverse this link and this link and this link. Why don't I do something now which will make future easier for me? Right? Future finds easier, that's the time. So what I do is that once I do this, yeah, I will maybe make another pass of this and now change the pointers to directly point to there. We don't know the root, no? We don't know where to make the. No, but when I am doing a find, I need to know where the root is. That's why I am doing a find in the first place, right? How do I know the root pointer? Only when I reach the root will I know what the root reference is. And so I need to make a second pass to update. Right?
So every time you are doing a find, you are updating the pointers.
Every time you go a find, you update the pointers. Okay? Yeah. Yeah. Right. Yeah, then there is no need. So for here instance, I did not change this, right? There is no point. What does it mean to change the pointer to this? This will be changed, right? Because it gives us. Yeah, the next time the picture is this. So we look at this picture and decide what to change and what not to, right? So again, when I go through here, what's the point in changing this? Because it's already pointing to the root. This becomes the picture. I don't have this picture anymore the next time. How do we directly go to the nodes in this tree? We keep a reference, right? For every node, when I'm keeping the node in this union find data structure, the node corresponds to a vertex of my graph. Right? I don't just create the union find data structure as a standalone entity. I have to link it up with my graph somehow. For every vertex, I have one node here. I keep a kind of a cross reference from the vertex in my linked list data structure, or adjacency list data structure in which I have the vertices. I would have a reference to the corresponding node in this union find data structure. right? So that when I have to reach a particular vertex, I can follow that reference and find out which connected component that vertex belongs to. Okay? So with that, we are going to end today's class on the union find data structure, and we are going to discuss another algorithm for computing minimum spanning trees in the next class.
हौसला छोड़ो ना हौसला दे दो ना हौसला जाना है दूर तुझे हौसला छोड़ो ना हौसला दे दो ना हौसला जाना है दूर तुझे सतरंगी समा है हाथ तिरंगी फिजा है क्यों है ना बोलो ना सतरंगी समा है हाथ तिरंगी फिजा है क्यों है ना बोलो ना हौसला छोड़ो ना हौसला दे दो ना हौसला जाना है दूर तुझे हौसला छोड़ो ना हौसला दे दो ना हौसला जाना है दूर तुझे सतरंगी समा है हाथ तिरंगी फिजा है क्यों है ना बोलो ना सतरंगी समा है हाथ तिरंगी फिजा है क्यों है ना बोलो ना
Chandigarh University Common Entrance Test.